In this video, we're going to be looking at how we calculate the average mass of an element, and we're also going to be looking at what ions are and how we calculate the protons, neutrons, and electrons when we have an ion instead of a neutral atom. So first of all, let's start off with average atomic mass. If you look at your periodic table, you're going to notice that the mass that's listed in each box usually has a decimal. That's because it is an average of many different isotopes together and not the mass of just one isotope. So it's a weighted average of all the different naturally occurring samples of that particular element. And the average is based off of all the isotopes that we find in nature. So sometimes an element might have 3 different forms, and they all have, again, the same atomic number, but their masses are different, so we average the masses together to get our, on our periodic table to get that average. The mass, if we did it in grams, would be really, really small, because think of how small an atom is. You can't even see it with your own eye, let alone trying to put it on one of our balance beams to get grams. It would be really, really small. So when we do the average atomic mass, we're going to be using a new unit called AMU, which stands for the atomic mass unit. And let's say that, for example, we have an average atomic mass for carbon. On your periodic table, we have 12.011. We can carry that out a little bit further. And so we know that that's an average because we definitely have some decimals there. So it's several different types of carbon that we have averaged together to get that mass. Because the mass is so close to 12, though, we can make a pretty good assumption that carbon-12, which is a type of isotope of carbon, is the most abundant one, since the mass is closest to 12 than 13 or 11. So we can get an idea of which one we probably have the most of in nature. And it's not a whole number, again, because it is an average. Alright, so some things that you're going to need in order to calculate the mass. You're going to need 3 things. First of all, you need to know how many isotopes there are. You need to know the mass of each isotope. And you also need to know what's the abundance of it. If we have 99% a certain mass and only 1% of a different type, well, then that needs to be calculated as well when we're trying to calculate our average mass. So for example, let's say that we have boron. This is atomic number 5 on your periodic table. There are 2 different types of boron, and you can see them here because of the top number here representing the mass. So we have boron 10, and that's found in abundance. 20% that you find in nature is boron 10. And the other 80% is actually boron 11. So boron 11 is 80% abundant, boron 10 is only 20% abundant. And so to calculate the average atomic mass, we would take the mass of 10, and we would want to multiply that by its decimal. What percent is that? It was 20%. So 10 times 0.2. And then we would want to add to that our other type of boron, which was boron with a mass of 11, and it is 80% abundant, and that is going to equal our average. So mathematically, 0.2 times 10 gives us 2, and 11 times 0.8 gives us 8.8. And notice I'm not worrying about significant digits right now, mainly because I'm taking a percent times a number. So I want to keep everything, I want to keep all numbers for right now, and I'm only going to look at significant digits right here when I'm adding these 2 together. 2 plus 8.8 gives me 10.8, but when I'm adding, I'm only allowed to keep the lowest number of decimal places, which in this case is 0 decimal places because of the 2. So I'm only allowed to keep to the ones place, no decimal places. So the 8 rounds up, and my average mass is 11. Not 10.8. 10.8 would be the mass if we were not including significant digits. The existence of isotopes, remember, these are the same element. They just have different masses. And so we do need to know what the average is it helps us to remember that there are multiple types of a certain element, that carbon isn't just one type of carbon, there's multiple forms and they just have different masses and different numbers of neutrons. So we're going to do two more examples here. Another practice problem, we have lithium. And lithium here has a mass of 6, here it has a mass of 7. So we're going to take our mass of 6 and we are going to multiply that by its abundance. And to get these out of a percent, you want to move the decimal over 2 places. So 0.075. And when we multiply that together, we get 0.45. So 0.45 is the mass of that. And then lithium 7, its abundance is 92.5%, so 0.925. And when we multiply those together, we get 6.475. Notice that that's definitely the bigger number, and that's because we find it in the greater abundance, so we would expect that one to be larger. Now we want to add these together, and so when we do, we get 6.925, but when we add, we're only allowed to use the lowest number of decimal places, which is 2. So in this case, we would have 6.93, and that is an AMU. Remember, that's our new mass. Since we don't want to use grams, that would be too small. This is an atomic mass unit. And let's our last one, we're going to do silicone. This one has 3 different isotopes. So we follow the same rules. We just have to do 3 problems and add our masses up. So we're going to take our mass of 28 and we're going to multiply that by its abundance of 0.9223. And that gives us 25.8244. We're also going to take our mass of 29 for this one here, and its abundance is only 4.67%, so that's 0.0467. And that one gives us 1.3543. And then our third isotope has a mass of 30, and it's not very abundant, only 3.10%, so 0.0310%. And that gives us only 0.93. When we add all of those up, we get a total mass of 28.1087. But again, our lowest number of decimal places is this one here with 2 decimal places. So in our final answer, we would say that our average is 28.11. The 8 here rounds up. And again, that's atomic mass unit. Now we also want to look at ions in this one as well. And an ion is a group of atoms, or it can be a singular atom, but it has a charge to it. So it has a positive or a negative charge. It's not neutral. So our protons and our electrons are not equal to each other. And when we take away an electron, that is going to give us what we call a cation. So a cation is anything that has lost an electron, and notice that it has a positive charge. When you lose an electron, that means that you now have more protons, less electrons, because one got taken away. So that gives you a positive charge. The reverse of that, if you add an electron, now that is called an anion. So 2 vocabulary words you definitely need to know. And an anion means that we've added an electron. So electrons are negative. You have more negative, less positives, so less protons. And so that's where the negative charge comes from, because you have more electrons. You can tell the difference between an atom and an ion by looking at our abbreviated form that we've been writing, and look and see if it has a charge next to the superscript. If it does, then that means that it is an ion. Forming these, we have 2 examples here of a cation and then one of an anion. A cation forms when you lose 1 or more electrons. So notice here we started with magnesium, and magnesium is going to lose 2 electrons. And so when it loses those 2 electrons, that means that it now only has 10 electrons here and 12 protons still. So that means that's where that +2 comes from, is because the protons are bigger. Same with the anions. Anions are when you gain an electron. So here we're gaining an electron. Now we have 10 of those, 10 electrons instead of 9. Because our electrons are bigger, we get the negative charge because electrons are negative. So we're going to do two examples. We're going to do the potassium and the oxygen, and then I'm going to have you do the calcium example. And when I walk around and check those, that one needs to be finished. So again, it said that you could look at your symbol and look and see if there's a charge. These all have a charge with them. So these are all examples of ions where the protons and the electrons are not equal to each other anymore. When this is set up, our numbers still mean the exact same thing. So this bottom number is still your atomic number. So your atomic number is your number of protons. So for potassium, that's 19. And if you want to look up potassium on your periodic table, you're going to see it's number 19. In order to get the neutrons, we still take our mass minus our number of protons, and that's going to equal our neutrons. And so we have a mass of 39, and we know we have 19 for our protons, and so our neutron number is going to be 20. And now the electrons are where we need to be careful. We have a positive charge. That positive charge means that we lost electrons, and if there's a number beside it that tells us how many that we lost, in this case it's just a plus, that would mean +1. So our protons are bigger by 1 and our electrons are smaller by 1. So our protons aren't going to be, our electrons are not 19 anymore. We actually only have 18 electrons, and that's because of the +1. We've lost 1 electron. Let's do oxygen. Our bottom number here again, our atomic number, so that is 8. And if we're doing our neutrons, we take our mass of 16 and subtract the number of protons. And so we also get 8 for our neutrons as well. Now for this one we have a -2. So negative means that we have gained electrons, and so we've gained 2. Not just 1, we have a -2. So instead of 8 protons, we've gained 2, so now we are at 10. Negative, your electrons should be bigger. If you have a positive number, your electrons should be smaller. So I want you to try this example, do the protons, get your neutrons, and then again you're going to need to take a look at that +2 and decide what you need to do with that in order to get your electrons. And I will be checking that in class when I walk around and check your notes.